Right. This is a short lecture just to review some of the things we've covered up till now, which is week 8. So we have sample here. You can see the sample standard deviation, which is the square root of the sums of squares, the sums of square deviations divided by n. And the variance would just be, you square that, you get rid of the radical. The estimated population variance, the square root of which will be the standard deviation, is just the sums of squares divided by the degrees of freedom, which is n minus 1. Remember that SPSS gives you estimated population values for variance and standard deviation. So if you're asked to calculate your z-score, a single score in a sample, from the class, from some class data, then you're going to have to use SPSS maybe to calculate the sums of squares, but then you have to calculate it by hand what the actual standard deviation is. Okay. All right, moving on. So a z-score is just a standardized score, and that's the value in standard deviations, right? Z of 1 equals 1 standard deviation. Then we covered correlation. We talked about Pearson's R for interval ratio or continuous data, or Spearman's rho for ordinal variables. Correlation, like regression, assumes a linear relationship, and correlation provides you with a standardized coefficient. And last week we covered regression, which provides us with the intercept, slope, and slope, which allows us to write out the regression line and predict a value of y for a given value of x. And we talked about r squared, or the sums of squares, regression divided by sums of squares total. So here are our variables for the correlation and regression. Let me get a pin here, right? Okay, so here we have, this is for Pearson's R. And we have the covariance of x and y, which is just multiplying the deviations of x times the deviations of y for a single score, and then adding all those scores up, all those values up, and dividing by n minus 1 of the degrees of freedom. To calculate Pearson's R, you divide the covariance of x and y by the standard deviations of x times the standard deviation of y, all right? We're standardizing that score. Anytime we divide by a standard deviation, we are standardizing to some degree, right? Then we have here the regression line. So y prime, or the predicted value of y along the regression line, is equal to the y-intercept plus the slope times x. You can calculate the slope just by dividing the covariance of x and y by this variance of x, right? And then you can calculate the y-intercept by subtracting the slope times the mean of x from the mean of y, all right? Next, we talked about formula for sums of squares, and we start with the sums of squares total, which is just all the variance in y. So it's just simply the deviations of y squared and then summed up, just like the sums of squares we see on the numerator of our variance, right? Okay. Then we talked about sums of squared regression, which is just that gain in predictive power we get from estimating a value of y based on the regression line, based on a relationship, rather than based on the mean of y. So this is just, it's called the sums of squared regression are explained, and it's a measure of how well the model fits the data. And it is just getting the difference between the predicted value of y and the mean of y, which is that gain and prediction, right? Squaring that and then adding them up. And then finally, we talked about sums of squared error, which is the difference between the actual value of y and what the regression line would have predicted, the predicted value. So you get the difference between the actual value of y and the predicted value of y and square it and sum it up. And that's also called sums of squared residual. All right, so this is all unexplained variance. In statistics, everything that is not explained by the model, in this case, it's just a simple regression model, all that variability that's not explained by the model is residuals, right? And then we can calculate r squared, or the proportion of variance explained by the model, by dividing the sums of squared regression by the sums of squared total. And we're going to come back to that when we talk about ANOVA in a couple weeks. Okay, so just to walk you through our example we've been using is moral identity related to aggression. The first way, the tool you guys had to look at this relationship was just to make a scatter plot add a regression line of best fit, and then look at that. And here we can see the line slopes down. It's a negative relationship. It looks like there's a relationship there. Next, we learned how to run a correlation analysis and get Pearson's R, which is negative 0.298, for that relationship, right? After that, we learned how to run a regression, right? Where you actually have more information. You get R squared, which is the proportion of variability in Y explained by X. You can get the slope, which is negative 0.44 in this case. We can see that negative 0.29, the standardized slope, is equal to that Pearson's correlation that we saw in the previous slide, right? And we also have here sums of squared, regression, error, and total, okay? So we can use that slope and intercept to write out the regression equation, right? So first we find the intercept, which is 5.56, and we find the slope, negative 0.44, and we can write out that regression line, and we can use it to solve for values of Y at different values of X, right? All right, so that's the sum of this review.